Welcome back to Materials Science and Engineering. And so we are going to be solving this problem. It is an excellent problem. It helps us really begin to think through strengthening of materials. But before I begin to solve it, I want to back up a moment and just talk about dislocations. So there are, this problem statement uses the word cold working, right? So we got a cylindrical, cold worked brass specimen with a certain ductility, and we know we're going to use this graph in a moment. After the cold working process is complete, here's its radius. What was the radius before cold working? So let's talk about cold working, since it was mentioned 3 times in the problem statement. All right, so cold working. First of all, its name describes it, right? So cold just means at room temperature. Working means we're deforming the material on purpose. And by material, I really mean metal, right? Because it's metals that we cold work in order to make them stronger. So we're deforming the material on purpose, not by accident. There are other words for this. Sometimes you hear it called strain hardening. These refer to the processes. You might even hear it called work hardening, right? So they're all very descriptive names, and I want you to understand how it is that that doing this to a part makes it stronger. So why does deforming a material on purpose, why does it make it stronger? Why does it make a metal stronger? All right. And so the answer to all of these methods of deforming of strengthening a material is that they hinder, which means slow down, dislocation motion. Or you might say that they hinder slip, which just means dislocation motion. And so why does that, how does this work, and can we explain it? So I've drawn a model of an edge dislocation over here. If you remember, edge dislocations refer to an extra half plane of atoms inserted into the lattice, and we indicate it's an edge by kind of drawing a little perpendicular sign there. This is a 2D model of what's actually going on in 3 dimensions. So if I was to try to have you envision the whole lattice stretching out behind it, right? So we would see atom after atom, extending on back, right? On back behind us. And so you can appreciate that this dislocation kind of ends on a line, right? So it's a linear defect, ends on a line, DEFECT, a linear defect. And so let's talk about what's happening in the vicinity of where that edge dislocation ends on that line that moves back in 3 dimensions in this crystal. So remember, we're not talking about packing dots. We're not packing dots. We're actually packing things that are atoms, right? And when you think about packing of like-sized spherical objects, think tennis balls in a box, right? They end up nestling into each other in this arrangement, which is called close packed, and we remember that from before. And slip likes to occur along these close packed planes. But my point is that there's no extra room around. They're touching each other, and so these little purple dots here are large atoms that are touching each other, and so These large atoms, when you have an extra half plane of atoms kind of squished in there, you're going to find a region of compression surrounding it. And you're going to find a region of tension immediately below it. There's a little bit of extra room for these atoms. There's really a little bit of not extra room above it. In other words, the crystal is distorted. Near the dislocation end, where near the line of the dislocation. In fact, you can envision this sort of green area as being like a cylinder of distortion moving through like a column, right? A column of distortion, and then it's immediately, near a column of another type of distortion called tension. Okay, and so why does this all matter? Well, it matters because it's basically a region of messed up lattice, and so. Big picture, right? Like, let's always kind of keep in mind what we're talking about. When we make a stress versus strain curve, we have that linear portion, right? Which is just bond stretching. It's recoverable. And remember, strain is equal to the change in length compared to its original length. This is just force per unit area. So when we are pulling on a part which has a certain area with a stress, right? When we pull on it, it gets longer, right? It gets longer in this quantifiable way. And once we exceed the yield stress or the yield strength of the part, we end up with a region of plastic deformation that can be very considerable. And then ultimately you have failure of the part, right? And some elastic recovery, and you have a final length of the part. So all this region, is what we're talking about. We're talking about what's going on here. Okay. And right, so we actually strengthen the part by doing this plastic deformation to a part. All right, let's kind of bring ourselves back to this problem statement. So the principle of cold working and strain hardening and work hardening is that you are deliberately adding, so I'm going to write it in a little circle here. We deliberately deform the metal. So what does this do? This dramatically multiplies how many dislocations that are present. This increases the dislocation density. And these kinds of dislocation densities, you can achieve values like 10 to the 10th per millimeter squared. There's a lot of them. And so the more dislocations you have, the slower other dislocations get. So if we have another dislocation kind of coming along, and I'll indicate it with a perpendicular line, it's trying to move that way. It can't get very close because it's going to encounter this compressive field and this tensile field, and it's going to be repelled, basically. It's going to be slowed down by the fact that there's already dislocation there. So this, as we add more and more dislocations, we actually move the yield strength up, right? So as we, if we plastically deform it to here and we unload it and we reload it, right, we actually end up with a stronger part with the same elastic modulus. We end up with a higher yield strength. All right, so let me return to the problem statement. Right, so we have cold worked a brass specimen, and afterwards it has a certain radius. So there's a key formula we need, which is the percent cold work formula, and it's easily it's just the initial area minus the deformed area, which will be smaller because we're drawing it down. That means making forcing a cylindrical part through an orifice that is smaller than it is, and this is called drawing because the part is drawn through, and so you end up with a smaller diameter. So we go from an initial area, right, to a smaller area as a result of this process of drawing it down mechanically. So that's kind of what's going on. So this is machinery, and the part goes from left to right, and it goes to a smaller diameter. So if the initial diameter is A0, the final diameter is AD. And so we're told the radius, the final radius, the drawn or the deformed radius. And so we can calculate AD. AD is just going to equal pi times the final diameter, which is 10.1 millimeters squared. So that will be pi r squared for the final drawn area, or the deformed area, the area after deformation. All right, so on this problem statement, we're going to 20% ductility, and we are going to look for its intersection with the brass curve because it's brass, and then we're going to read down. That looks like about 22% to me. And so to solve this problem, we will write 22 is going to equal pi times the initial radius squared, right, minus pi times 10.1 squared divided by pi times the initial area squared times 100. Doing just some simplification, we can say that 0.22 is going to equal, looks like all the pi's cancel out. We will have r naught squared minus 10.1 squared divided by r naught squared. And if you carry that through, you will find that r naught is equal to 11.44 millimeters. But the main thing I wanted you to learn in this problem is why this all happens. And so I want to kind of summarize this by, let's go down to here. So this experiment, right, is a stress versus strain curve. With no cold work, we have a certain yield strength, right? Which we could see from this diagram, right? With no cold work, we had a ductility of whatever it was, right? And so the ductility on that diagram was some sort of very long length with a lovely ductility of like 66% or something like that, right? And remember, ductility is defined as being the final length minus the initial length divided by the initial length times 100. So that's the percent elongation or the ductility. And remember, strain is just LF minus L naught over L naught, right? So we can use the point at which it breaks and after we elastically recover it, right, to calculate the ductility. So with no cold work, we have a certain ductility, okay? With 10% cold work, we will have an increased yield strength as a result of the cold work, and we will have less ductility, right? So it fractures before the other one did, before the one with no cold work. With increasing amounts of cold work, right, we're fracturing earlier and earlier, but our yield strength is increasing. And so the bottom line is there's always this trade-off, right, between ductility and strength. Because of the fact that, we strengthen it by inserting dislocations, for example, and when we do that, it's just less ductile. All those dislocations get all so tangled up that the part can't deform as much as it could without any cold work, and it fails. All right, well, let's wrap it up there. Thanks very much.